This is an introductory lecture on regression analysis. Though we'll discuss very simple concepts here, these form basis of the topic regression analysis and hence should not be ignored. First, we provide a list of non-exhaustive prerequisite topics for this course. By non-exhaustive, I mean that I'm not covering all the prerequisite topics, but try to cover at least 95% of them. From probability theory, we mainly need the following topics. In regression analysis, we often need to compute expectation and variances of different statistics, for which it is important to have very clear concepts in first 5 topics, that is random variable, distribution function, probability density, and mass functions and their properties, expectation and moment generating function when they exist, well-known discrete and continuous probability distributions such as binomial distribution, Poisson distribution, normal, Cauchy, gamma, beta distribution, exponential distribution, and their properties as well. Random vectors, joint and marginal probability distributions, conditional probability, conditional expectation, and independence, and what happens to conditional probability and conditional expectation if two random variables are independent. In regression analysis, we often perform testing of hypotheses which need knowledge of topics 6 to 8. That is function of random vectors, because there we often need to find out distribution of the test statistics under null hypothesis and alternative hypothesis, and for that we need to know function of random vectors and how to find out the distribution PMF or PDF accordingly of the function of the random vectors. Also, we need to know multivariate normal distribution and its properties, chi-square distribution, T and F distributions. To judge asymptotic performance of the proposed test and estimator, we also need knowledge from topics 9 to 11, that is modes of convergences, distribution convergence or weak convergence, convergence in probability, almost sure convergence, this kind of convergence, or convergence in LR sense or in L-earth moment, that kind of convergence we need. Also, we need weak law of large numbers, strong law of large number, central limit theorem for a sequence of independent random variables, and delta method and Cramer-Wald device. So all these topics you already studied in SI 417 course in the last semester. Therefore, you are expected to revise these topics to start with regression analysis course. From linear algebra, we mainly need the following topics which you already studied in SI 423 course in the last semester, and hence you are expected to revise them to start with the regression analysis course. Following topics are needed from statistical inference, and this course, that is SI 402, is running parallelly to the regression analysis course in this semester, but most of the topics are also included in the JAM mathematical statistics syllabus, and you already qualify this exam. Henceforth, you are expected to revise these topics to cope up with the regression analysis course. You will learn these concepts in more depth in SI 402 in this semester. Multiple linear regression model can be expressed as Gauss-Markov model, where we need to estimate model parameters unbiasedly and need to deal with best linear unbiased estimator and maximum likelihood estimator of the model parameters. So therefore we need concepts of topics from topics 2 to 5 here, that is mean square error, unbiased estimator, linear estimator, and base linear unbiased estimator, maximum likelihood estimator. Performing testing of hypothesis on model parameter needs knowledge of the topics given mostly the 7. So this is the critical region, what is type 1, type 2 error, level and power of the test. Now, construction of confidence interval for the model parameter also need the concepts from the topic 11, that is construction of confidence interval. Those who are not very much comfortable with these topics can avoid minimum variance unbiased estimator, most powerful, uniformly most powerful unbiased tests, likelihood ratio tests, and asymptotic tests at the starting level, but need to make up uh, all these topics very quickly, at least before the midsem. In case of any difficulty, please feel free to discuss with me. So these are the prerequisite topics that we need for regression analysis course. Next, we discuss the objective of regression analysis. Regression analysis is a collection of statistical techniques for investigating and modeling relationship between two or more than two variables. For example, one may wish to examine how the cigarette consumption of a particular state in a given year depends on different socioeconomic and demographic variables. For example, average age, educational qualification, and annual income of the consumers, and price of cigarettes. As another example, one may wish to examine how the production of paddy, suppose production of paddy of a state depends on different geographical variables. For example, location of the state, soil condition or fertility of the soil, rainfall, temperature, etc. So this is another example where we are interested in the relationship between uh, two or more than two variables, like whether production of paddy is related to all these geographical variables. Also, one may think of another example. For example, uh, so in water pollution, so whether the nitrogen concentration in a particular river depends on land distribution or the distribution of land uses of the locality. For example, how percentage of land used for the industrial purpose, percentage of the land used for the agricultural purpose, percentage of the land used for the residential purpose, and a percentage of the land which is uh, which is in the forest. So all these cases, we actually interested in the relationship between more than two variables. So there are actually plenty of such examples that emerges from different fields of science, including biology, medicines, economics, finance, business, demography, geography, agricultural science, chemistry, physics, meteorology, engineering, education, sports, sociology, and psychology. The relationship between the above mentioned variables is expressed in the form of an equation. The variables which are of main interest, or in other words which we want to explain, is called response or dependent variable. Also, the variables which help to explain the response variable are called explanatory variable or predictors. In the above example, as you can see, the response variable is the cigarette consumption, whereas the predictor variables are age, education, income, price of the cigarette. In the second example that I discussed, there the response variable is production of paddy, whereas the predictor variables are location, fertility of the soil, temperature, and rainfall. In the third example, the response variable is the nitrogen concentration in the water of a particular river, whereas the predictor variables or the explanatory variables are the percentage of land used for the agricultural purpose, for the residential purpose, for the industrial purpose or commercial purpose, or the percentage of the land for the percentage of land in the forest. So the so 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 we know what is the response variable and what is the predictor or explanatory variable here. And so we usually try to explain the response variable in terms of or as a function of the explanatory variable or the predictor variables. So we usually express this relationship in the form of an equation. The predictor or the explanatory variable are also called by other names such as independent variable, covariate, regressors, and carriers. The name independent variables is least preferred because in practice the predictor variables are really independent of each other, and we know what is the meaning of the independent. So if two random variables are independent, that has some different meaning, and it has it is a technical word. So it's better to avoid the avoid the word independent variables unless the predictors are really independent. The term regression was coined by Francis Galton in the 19th century to describe a biological phenomenon. For Galton, regression had only biological meaning, but his work was later extended by Yule and Carl Pearson to a more general statistical context. Since then, regression methods continue to be an area of active research. In recent decades, new methods have been developed for robust regression, regression involving correlated responses such as time series and growth curves, regression in which the predictors and the response variables are curves, images, graphs, or any other complex data objects, regression methods accommodating various type of missing data, non-parametric regression, Bayesian method for regression, regression in which the predictor variables are measured with error, regression with more predictor variables than observations, that is high dimensional regression, and causal inference. These are all the recent or the very hot research topic in this decade. Regression analysis is primarily used for two conceptually distinct purposes. First, regression analysis is widely used for prediction and forecasting, where its use has substantial overlap with the field of machine learning. Second, in some situations, regression analysis can be used to infer causal relationship between the explanatory and the dependent variables. Importantly, regressions by themselves only reveal relationships between a dependent variable and a collection of explanatory variables in a fixed dataset. To use regressions for prediction or to infer causal relationship respectively, a researcher must carefully justify why existing relationships have predictive power for a new context, or why a relationship between two variables has a causal interpretation. The latter is especially important when researchers hope to estimate causal relationship using observational data. Next, let's discuss a few notation and the basic philosophy behind the regression model. We denote the response variable by y and the predictor variables by x1, x2, and in this way up to xp, where p denotes the number of predictor variables. Mostly, it is never possible to obtain the true relationship between the response and the predictor variables. A regression model can only approximate this relationship. For example, here we have y equal to this function of x1, x2 up to xp plus epsilon. So this actually approximates the relationship between the response variable and the predictor variables. We are not saying that it is a true relationship. It can only approximate the true relationship. Where the function f describes the approximate relationship between the response and predictor variables. Of course, f is a function of the predictor variables x1, x2 up to xp, but it also involves some model parameters as it is written here, beta 1, beta 2 up to beta r. The number of parameters involved in the model, that is capital R, may not be equal to the number of predictors, that is P. For example, suppose P equal to 1. So we have only one predictor variable, say X, and we have only one response variable, Y. So suppose Y equal to alpha plus beta X. So this is a linear model plus epsilon. So your F is, so it is F alpha beta X. So it is alpha plus beta X. So here you can see that here R equal to 2, whereas P equal to 1. So this is the case where R is greater than P. Also, we can think of the situation where it is just if Bx, so it is just, for example, beta X. In that case, we have R equal to 1, that is equal to P. Also, we can think of, so for example, suppose we have P equal to 2. Suppose we have x1 and x2, two predictor variables and one response variable y. And I'm writing y equal to e to the power beta x1, x2. So in this case, you can see that R equal to 1, there is only one model parameter, that is beta, whereas P equal to 2. So in this case, we can have R is less than P. So all the situation can happen, that is R less than P, R greater than P, R equal to P. All of them can be, all of the possibilities are actually can happen. So the number of parameters in the model and the number of predictor variables, these two are different. So a regression model or a function which approximates true relationship between response and the predictor variables, that has two things. One is it is also a function. It is a function of the predictor variables, as well as it involves the model parameters which we actually want to estimate using our observed data. So that is basically the inference part, or the where we need statistical inference to estimate or to infer about the model parameters. So these model parameters are beta 1, beta 2 up to beta R. So what I have mentioned, that these model parameters are usually assumed to be unknown and are estimated based on observed data. Another component of the regression model is the random error, which accounts the variation or uncertainty in the response variable that is not explained by the predictor variables. In other words, it measures discrepancy of the function f to approximate the response variable. It is a very important component in a regression model, as its nature decides appropriate statistical technique to be used for the statistical analysis. For example, if the random errors are IID Gaussian, we usually use a least square method, whereas if the random errors are IID Laplace distribution, we often use least absolute deviation method. So depending on the nature of this random error, we usually decide the statistical techniques or the tools that we'll use. So as an example here, we can mention the linear regression model in P predictors as follows. So y equal to, so for example, it is beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 beta p xp plus epsilon, where epsilon is a random error, beta naught up to beta p, they're all model parameters, and x1, x2 up to xp, they are all predictor variables, and y is our response variable. So this is an example that, the special case we have already discussed, and as you can see that it has p plus 1 many model parameters in pre-predictor variables. And this model parameters beta naught, beta 1 up to beta p, that we need to estimate from the observed data because they are unknown. Now suppose we fix the value of the predictor variables x1, x2 up to xp. Then uncertainty or the stochastic properties of the response variable are completely determined by the random error. So if x1, x2, xp's are fixed, so therefore this part of the model is fixed, and given the value of x1, x2, xp, we know what it is. Now the randomness of y is coming from this random error per epsilon. For example, suppose the expected value of this random error is 0. Then it is easy to see that conditional expectation of y given the predictor variable, some value of the predictor variables x1, x2, xp, it is given by this. Because expectation of y given x1, x2, xp will be expectation of this quantity given x1, x2, xp. As this quantity only depends on x1, x2, xp, nothing else. So this term will treat as a constant, and expectation of epsilon doesn't involve x1, x2, xp. So therefore it is independent of x1, x2, xp. So therefore expectation of epsilon will be 0. And hence the conditional expectation of the response variable given the predictor variables is coming out to be the regression function that approximates the true relationship between response variable and the predictor variables. So therefore we can say that regression model actually determines relationship between the predictor variables and the conditional expectation of the response variable given the predictor variables. So those who are not familiar or who are not very much comfortable with the conditional expectation, please go through the material of SI 417 go through this concept from there. And also you can see any standard basic probability book, for example the book by Rohat and Saleh, for these concepts as well. Next we discuss steps in regression analysis. This discussion will provide you the way of exploring regression analysis techniques given a real life situation. Later, we'll be more involved in learning different regression models, their inference and analysis. But the importance of those learning and the appropriate way of their use for a given data set are discussed in these steps. These steps basically form a bridge between the theoretical and applied field of regression analysis. These desirable steps are as follows: statement of the problem, selection of potentially relevant variables, data collection, model specification, choice of fitting method, model fitting, model validation and criticism, and finally the conclusion. Now we illustrate the purpose and objective of these steps one by one. So first we start with statement of the problem. So statement of the problem, what is our objective? To state that is very important, because an ill-defined problem or a misformulated question can lead to wasted effort, selection of irrelevant set of variables, wrong choice of statistical method of analysis, and finally the wrong conclusion. So here is an example. So suppose we wish to determine whether or not an employer is discriminating against a group of employees, say women. And data on salary, educational qualification, and gender of employees are available in company's record. And we wish to determine whether the employer is discriminating against a group of employees, say women. So discrimination occurs when on the average, so there are different concepts of discrimination between discrimination against a group of employees. So here I am considering two of them. So discrimination occurs when on the average women are paid less than equally qualified men, or women are more qualified than equally paid men. So in this two way there can be discrimination. So to answer one, we need to set salary as our response variable and gender and educational qualification as predictor variables. Whereas on the other hand, to answer B, we need to set educational qualification as response variable and salary or gender as our predictor variables. The selection of variables depending on the nature of the question we wish to answer. So therefore, first we need to clearly state our objective or the question that we want to answer. And then accordingly, we have to specify which is our response variable and which is our predictors variable. And then only we can go for the collection of data. So the second step is in the regression analysis is selection of potentially relevant variable. So now we know the basic, we know very clearly what is our objective and what is the question that we want to answer in the previous step. Now what we'll do in the next step, after stating the problem clearly, now we select the set of variables that can well explain the response variable. So we first select what is our response variable, and then we select the set of variables which can explain our response variable. A regression equation containing only one predictor variable is called simple linear regression equation. Sorry, it's not linear. I was wrong. So a regression equation which contains only one predictor variable is called simple regression equation. If it is linear, then it is linear, but it may not be always linear. So it is just called simple regression equation. A regression model containing more than one predictor variables is called multiple regression model. When we deal with only one response variable, the regression analysis is known as univariate regression analysis. In certain applications, the response variable can actually be a set of variables. When we have two or more than two response variables, we call it multivariate regression. Throughout this course, we deal with univariate regression both in simple and multiple regression setup. So depending on the number of predicted variables, regression analysis can be divided in two parts, simple and multiple. So one predicted variable is for the simple regression model, and more than one predicted variable is for the multiple regression model, whereas the number of response variable is divided into actually divides the regression analysis in two parts, univariate and multivariate. So one response variable goes for the univariate regression analysis, and more than one response variable goes for the multivariate regression analysis. So here we'll deal with only one response variable, that is we always deal with univariate regression, but we'll deal with one predictor or more than one predictor variable. So we deal with both simple and multiple regression model as well. So after stating our problem, so in the next problem is to clearly state what is our response variable and what is the explanatory variable that we'll deal with, and accordingly what is our regression model, whether it is simple regression model or the multiple regression model. Now the next task is to collect data. So data are collected on the response and the predictor variables which are selected to be potentially relevant in the previous step. The data may be either experimental or non-experimental. So suppose we want to decide dose of a particular medicine on the high blood pressure patients, for example. Suppose we have 50 such patients for the experiment. Thus, we can randomly divide these 50 patients into three groups and apply low, medium, and high dose of the medicine in these three groups. Based on the outcome, we can decide on the appropriate dose of the medicine. Note that this is a planned experiment and we can choose the patient not having any other medical complications which control over the external factor of the experiment. Such a kind of data is called experimental data, where we have control over the other external factors. Non-experimental data is as follows. Suppose we try to see dependence between nitrogen concentration in the water of river and the distribution of the land uses in that locality. Other external factors like heavy rainfall or heavy temperature may affect our data and consequent statistical analysis. And here we do not have any control on these factors. Such data is called non-experimental data. So our data may be either experimental or it may be non-experimental. In either case, we always record our data as follows. So you can see in the table, so we are considering n observations. So we have n subject here, and for each of the subject we are observing our response variables and the predictor with many predictor variables. So corresponding to subject 1, we consider the observed value of the response variable y is y1, and the observed value of the predictor variable x1 is x11. Observed value of the predictor variable x2 is x12, and in this way the observed value of the predictor xp is x1p. Similarly, for the ith row, that is corresponding to the ith subject, the value of the response variable y is yi, and the value of the predictor, the first predictor variable is xi1, and in this way, the value of the jth predictor variable is xij. So here the notation, yi is the value of the response variable y corresponding to the ith subject, and xij is the value of the jth predictor xj corresponding to the ith subject. And you may note that the values I am here here I am denoting by the small case, whereas the variables y, x1, x2, xp, they are all I am using in the capital letter, but their values I am here using the small letter. And in xij, so here the first suffix is used for the subject or the observations, and the second suffix is used for the predictor variable. So this convention will be followed throughout this course. Each of the variables, so you can see that either y or x1, x2, xp, each of the variable can be classified as either qualitative or quantitative variables. So as a quantitative variables, you can think of price of a house, number of students, concentration, nitrogen concentration of the river, cigarette consumption. You can think of, in this way, you can think of many other examples. As a qualitative variable, you can think of blood group, educational qualification, hair color, color of flowers, and so on. For the purpose of computation, qualitative variables are usually coded into a set of indicator or dummy variables. So for example, so here I'm considering, so suppose there are two kind of people, for example, and their hair color is, for example, red, not red, so sorry. So suppose their hair color is black, brown, and suppose gray. So these are the hair colors that we have, or maybe we can take white as well. So this is a qualitative variable, and it has 4 categories, for example. So what we can do, we can define a dummy variable, 3 dummy variables instead of this categorical variable. So there are, suppose, x1, x2, x3. These are all the dummy variables corresponding to the 4 categories. So if a qualitative variable has k category, then we'll consider k minus 1 dummy variable to code this qualitative variable. So here we have 4 categories, so I'm defining 3 dummy variables. So for the black, I'm considering 1, 1, 1. So if all the values of x1, x2, x3 are 1, then we think, so that corresponds to the hair color black, and 0, 0, 1, that corresponds to the color brown, 1, 0, 0, that corresponds to the color gray, and 0, 1, 0, that corresponds to the color white. So for example, so in this way, actually we can consider all this. So it's basically, so here we should not actually use 1, 1, 1, because if we add these 3 rows, we'll get 1, 1, 1. So it should not be like this. So these 4 rows should be actually linearly independent. So you know what is linearly independent. So you already learned this in linear algebra class. So what do you mean by linear independent vectors? So these 4 row vectors should be actually linearly independent. So except if we don't have the null vector, so maybe we can write here 0. So if we have all the entries to be 0, then we can say that it is black. Otherwise, if 0, 0, 1, then it is brown. Gray if 1, 0, 0, and 0, 1, 0 if it is white. So we should avoid 1, 1, 1, and instead we prefer to have it 0, 0, and 0. So in this way, we actually usually code the qualitative variable in terms of indicator or dummy variable. So we'll discuss this procedure in more details in our regression analysis course and at appropriate time. So this is basically a overall concept or overview of the regression analysis, the topic regression analysis. So I'm roughly mentioning it here. So this is how we collect our data. So first we state our problem very clearly, and then based on the problem, we decide what is our response variable, what is the explanatory variable that we'll consider, and then we collect our data for this predictor variables and the response variable. And how we record this data that is with this table. And we have already discussed the corresponding notations and etc. The next step is model specification. So now we have data. Now based on that data, we will specify our model. So this is basically the task to choose the function, the regression function that we already discussed in the previous slide. So it is a function of the predictor variables as well as it has some model parameters. So we have to choose this function. This function can be classified into two types, linear and non-linear. An example of linear function is as given here. So here I'm taking p equal to 1. So and it is a linear function between the response variable y and the predictor variable x1. So an example of nonlinear function is given by this. You can see that easily that it is a nonlinear function because e to the power something is a nonlinear function. A linear or nonlinear does not describe the relationship between y and x1, x2, xp. So what is the relationship between y and the predictor variable, response and the predictor variable? That doesn't decide whether the model is linear or nonlinear. So what decides whether the model is linear or nonlinear? It is the regression, whether the regression model is linear and nonlinear with respect to its parameters. So to decide whether a regression model is linear or nonlinear, we'll look at what is the relationship between the response variable and the model parameters, not the predictor variables. It can be nonlinear in the predictor variable, still the model can be linear. So for example, each of the following models, you can see these are all linear models because they are all linear in the model parameters. So here y is linear in beta naught, beta 1 and beta 2. So it is, the response variable is linear in the model parameter. So it is linear. Here it is linear in beta naught, beta 1. So it is linear model. Whereas the actual relationship between y and the predictor variables that are nonlinear, you can see here we have the term x square and here we have the term log x. So it doesn't matter whether y and the predictor variables are nonlinearly dependent or linear dependent. That doesn't imply whether the regression model is linearly dependent on whether the regression model is linear or nonlinear. By convention, linear regression model is basically means whether the model is linear in the model parameters or not. So this is just by convention. So also I can mention a model. So y equal to, for example, I'm writing it like okay. So look at this model. So in this model, you can see that it is not linear in beta naught and beta 1. So it is linear in beta naught, of course, but it's not in linear in beta 1. So from that, you can say that it is a nonlinear model, whereas this is a linear model because these are all linear in the model parameters. All nonlinear functions which can be transformed into linear function are called linearizable functions. For example, here I have y equal to beta naught plus e to the power beta 1 x, for example. So that can be linearized because if we take log y, so it will be here log beta naught plus beta 1x. So now it is linear in model parameters log beta naught and beta 1. So we have to reparameterize our parameters. So instead of beta 1, I am taking log beta naught. Instead of beta naught, I am taking log beta naught. So this model log y equal to log beta naught plus beta 1x. So log y equal to log beta naught plus beta 1x. So this model is linear in the parameter log beta naught and beta 1. So therefore it is a linear model, and this model y equal to beta naught plus e to the power beta 1x, this is a linearizable model because it can be transformed into a linear function or a linear model. So the class of linear models also includes linearizable functions, but all the nonlinear function cannot be or may not be linearizable. For example, this model cannot be expressed as a linear model. It cannot, so there doesn't exist any transformation which transform it into a linear function. So therefore it is a pure nonlinear model. So next, after collecting the data, looking at the data, we have to decide whether a linear model or a nonlinear model or linearizable model will explain our response variable in terms of the predictor variables that we are considering. So this is the main objective of this step, model specification. The next one is method of fitting. So once we decide about our model, regression model, so what we have y equal to f beta 1 beta 2 beta r x1 x2 xp plus epsilon. So this is our regression model. So once we specify this model, so we know what is f, we already have the data on y, x1, x2, xp. Now the next task is to find out or to estimate the model parameter beta 1, beta 2, beta r, because they are unknown to us. So after the model is specified and the data are collected, the next task is to fit the model or to estimate the unknown parameters in the model, that is beta 1, beta 2, beta r. The most commonly used method of estimation is called least square method. Under certain assumptions, this method produces estimators with desirable properties, like often it is unbiased estimator, often it is base linear unbiased estimator, that is blue, often it is maximum likelihood estimator. So there are very good properties of this estimator we can have under certain assumptions. But in some instances, other estimation method, for example, the maximum likelihood method, ridge and least absolute deviation method, works superior than the least square method. So these are basically so this deviation from the least square method is the different part of the different branch of the regression analysis. For example, the robust regression, it may be, or it may be the constant regression. So the or the penalized regression. So these are all the different branch of the regression. So that is discussed in that specific branch of the regression. So here is the overview. So after selecting the model, we have to decide the method of fitting. So which method we'll use to estimate our model parameters. So that depends on the assumption on the random error that we already discussed. So if it is Gaussian, then we'll usually use the least square method. If it is a Laplace distribution, then we can use the least absolute deviation method. And there is plenty of such thing or deviation can happen. So the assumption can be on the random error part. The assumption, I mean, depending on the model assumption. So after deciding the model, we have to decide the model assumption, underlying model assumption. Based on that, we have to decide which method we'll use to fit our model. Now the next task is to fit the model. So we decide what method we'll use to fit the model. Now we'll fit the model. So in this step, we estimate the model parameter based on the collected data using the chosen fitting method that we actually select in the previous step. So let beta 1 hat, beta 2 hat up to beta r hat be the estimate of the parameters beta 1, beta 2 up to beta r. Then the fitted regression equation can be written in this way. So note that here we cannot write like y f, then beta 1, beta 2, beta r, then x1, x2, xp. That we cannot write because we don't know beta 0, beta 2 up to beta r. But we can estimate it using these hat estimators. Now the fitted regression equation. So these are all the terms that we need to use appropriately. So the fitted regression equation is given by y hat. So here we cannot write y because we are also fitting our response variable. So therefore we have to write y hat. That is actually equal to the same function of the explanatory variables with the model parameter replaced by its estimator. Beta 1 hat, beta 2 hat up to beta r hat. So the fitted regression model is given by this. We can compute n many fitted values of y, that is yi hat, and these are given by this. Note that here as we are considering the value, fitted value or the observations, we always use a small letter. And when we are using this hat, please be careful about that. So here we are using hat because we are considering the estimator. Here we are using the fitted value. So here we are using hat. So please be careful about the uses of hat. The residuals corresponding to the above fit is given by the actual value which we observe, that is yi, minus its fitted value, that is yi hat. So whatever we will get, that is called the residual for the ith subject, and that is denoted by ei here. We can predict the value of y for any given value using the equation 1. So suppose we are given some arbitrary value of x1, x2, xp, and given that value we can use this equation to predict some value for y. But it is not generally recommended to predict the response variable for a set of values of the predictor which are far outside of the range of our data. So for example, so this is suppose the x variable, the predictor variable, and this is the response variable, and we try to explain y in terms of x as a function of x. And suppose we are in our data, we have some x values within this range, for example. And here we are feeding some curve for y against x, and we have some model f, suppose for example beta x, and that model and that f is the curve of this, or the graph of this f is given here, for example. So suppose we are given some value of x here for which we haven't observed any y. From this fitted value or this fitted equation, we can find out, or we can give some prediction for y. But suppose we are asked to find out, or we are asked to forecast some value of y for the x value which is far away from the range that we observe in our data. And it is not recommended to use the same function for that value of x, because I mean in this range of x, this function may not be valid, or this type of relation may not be valid. So therefore it is always recommended to predict the value or to use the fitted equation within a small neighborhood of the range of our data. So now in this way we'll fit our model. So here there are some technical words, so please be familiar with this. What is a fitted regression equation? What is the fitted value of the response variable? What is the residuals? So these are all the technical terms that you need to be familiar with, and also the uses of hat, that also you need to be familiar with. So after model fitting, what we'll do, so after model fitting, usually we can go for the conclusion, one may think, but it's not the correct step to do. Before conclusion, we need model validation and criticism. So as you can see that when we are considering our model, so when we specify our model and we specify the method of fitting, there we consider some assumption for the model, and based on that we use our we fit our model. For example, whether the random error is Gaussian or not, whether random errors are independently and identically distributed or not. So there are few assumptions that we consider on our for our model, and based on that we choose our fitting method. Now we need, after we get our result, now we need to judge whether our assumption is actually correct or not. We need to validate that. And the validity of the statistical method in regression analysis depends on certain assumption made about the data and the model that I already discussed, and the accuracy of the analysis and the conclusion derived from an analysis depend crucially on the validity of this assumption. If this assumption doesn't hold, then this analysis or whatever fitting we have done, that is that we cannot use, and that will give us a wrong conclusion, or this can mislead us. So therefore, before using the fitted equation for any purpose, we first need to determine whether the specified assumption holds or not. Validity of this assumption be made before any conclusion are drawn from the analysis. So regression analysis is viewed as an iterative process. So we need to validate our assumption. So what we'll do, we will validate our assumption, and suppose it is correct and we see that yeah, so this is a reasonable assumption, then we can conclude based on the fitted model. But if it is not correct, or if it is not validated, then what we'll do, we'll modify our model, and based on the modified model we'll again fit our regression equation, and then we'll again validate our model, and in this way we'll go on unless we get some satisfactory output. So the regression analysis is viewed as an iterative process in which the output are used to diagnose, validate, and criticize, and possibly modify the inputs. So you can see, so for example, suppose here I'm writing all my inputs. So here, for example, I have data, model, and assumption. Assumption and suppose methods. So statistical methods, for example. And here, suppose I have output. So as an output, I have the fitted equation and some statistical inference also we can have. Now what we'll do, so we have this input and based on our assumption, model specification and methods, we'll fit our equation. So that we'll do, calculate. Now based on our output, we validate whether this assumption that we assume here in the inputs, whether these are true or not. So we validate. If it is not true, then we modify, validate and modify. We'll modify our model, and based on this modification model, again we calculate our fitted equation and we'll do inference. And based on that, again we'll see whether that modified assumptions are correct or not. We validate that, and if it is not correct, then we modify and again we go back. And in this way, we'll perform these iterations again and again unless we get the satisfactory output. By satisfactory output, I mean so the output which fit our data reasonably well and which satisfy our model assumption as well. So this is the satisfactory output. And after we get the satisfactory output, now we can draw our conclusion based on our last fitted model for which we get the satisfactory output. So this is the overall, this is all the steps of the regression analysis. So given a data, you need to go through all these steps. Given a real data, you have to go through all these steps. First, you have to see or you have to state what is the problem that you want to answer. Second, you have to choose your response variable and the predictor variables. You have to collect your data, or you may have the data in your real data set, for example. And then you have to specify your model. For that, you can use some graphical tools and etc. to specify your models, whether it is linear, nonlinear, or whatever. And and you have to set some model assumptions. And based on this assumption and the model, you have to decide about the fitting method. And using that method, you have to fit your model. And after you fit your model, you will get some output. And based on that output, you need to validate whether the assumption that you consider is correct or not. If it is correct, we are fine. If it is not correct, then we have to modify it. And again, we have to decide about the method of fitting. And then we have to fit. And again, we have to get the fitted model. And then again, we have to validate our modified assumption that we consider in the second step. And in this way, it will go on iteratively unless we get the satisfactory answer. And the satisfactory answer, the satisfactory output is an estimated model that satisfies the assumptions, whatever assumption we have considered, and fit the data reasonably well. And based on this satisfactory output, we can conclude whatever we want to conclude. So before, if we don't have the satisfactory output and we conclude something on the basis of that model, then or the fitted model, that can lead us that can mislead us, and we can have the wrong conclusion based on that. So this is basically how to perform the real data analysis given a data set using the regression tools. So when we'll go for the data analysis project in this course, you have to actually follow all the steps. And whatever you have seen here, so how to fit a model, how to infer about the model, and how to diagnose or validate your assumption, that is the main thing that we'll cover in this course mainly. Next, we discuss few notation which we use throughout this course. More notation may be added later if needed. Accordingly, I shall add some more slides in this lecture under the heading notation. So please be updated with the list of notation time to time. So we first start with R, which is a set of all real numbers. Throughout this course, so a matrix is denoted by bold uppercase letter, and suppose A is a matrix, then its transpose is denoted by bold uppercase A with the superscript prime. Bold 1 with the suffix n is a vector of length n whose all entries equal to 1. Bold 0 with the suffix n is a vector of length n with all entries equal to 0, and both these vectors are column vector. A n cross m matrix with all entries 0, that is a null n cross m null matrix, is denoted by bold sign O with the suffix n cross m. Bold upper letter I with the suffix n is the n cross n identity matrix whose all diagonal entries are 1 and off diagonal entries are 0. So now we'll consider diagonal matrix. So diagonal matrix is a square matrix whose diagonal entries are maybe 0 or may not be 0, but whose off diagonal entries must be 0. So a diagonal matrix of order P with diagonal entries A1, A2, AP is denoted by this notation. So here we have to maintain the order. So the ith diagonal entry of this matrix will be the ith entry of the set that we mentioned. So these entries cannot be permuted in the matrix or on the matrix diagonal. So we have to maintain the order. Ordered eigenvalues of a P-cross-P real symmetric matrix A is denoted by this. So here we have real symmetric matrix A, and we know that real symmetric matrix always has real eigenvalues. So therefore, order has its, ordering is meaningful. So the ordered eigenvalues, the set of ordered eigenvalues is given by this, and here also we have to maintain the order. So therefore, lambda 1 is the largest eigenvalue of A, lambda 2A the second largest eigenvalue of, and in this way we'll have lambda P as the smallest eigenvalue of A. But note that here equality can occur. So the repeated eigenvalues are included here. So suppose a matrix A has 4 eigenvalues, 2, 3, 3, 4, for example. So suppose the eigenvalues are 2, 3, 3, 4. Then our lambda 1 A will be 4, lambda 2 A will be 3, lambda 3A that will be also 3, and lambda 4A that will be 2. So the repetition or the equality of the eigenvalues is allowed. So we'll repeat that eigenvalues here as well. We don't omit that repetition. Now a P cross P real symmetric matrix A, we define diagonal matrix which is denoted by capital lambda with the suffix A, and it's diagonal entries, and its diagonal elements are the eigenvalues of A with the order. So the jth diagonal entry of the matrix lambda A will be the jth largest eigenvalue of A. Therefore, in our example, so it was 2, 3, 3, 4. So our lambda A will be so diagonal matrix. So first will be 4, the largest eigenvalue, then the second largest eigenvalue. So both of them, second and third, both of them are same. And at the end, the smallest eigenvalue or the fourth largest eigenvalue. So lambda A will be like this, and 0, the off diagonal entries are all 0. So this is the notation for this is the notation lambda A. Next, VJA, this denotes eigenvector A corresponding to the eigenvalue lambda JA. So here we'll consider always the real symmetric matrix A, and we'll talk about its eigenvector. So I know that there is no meaning to say that VJA denotes the eigenvector corresponding to lambda J, because we may have more than one eigenvectors corresponding to a particular eigenvalue. So here what we'll do is, so if we suppose A, so A is suppose real symmetric, then all its eigenvalues are real, and so therefore it will have P linearly independent eigenvectors, and we can orthogonalize it, or we can perform Gram-Smith orthogonalization on that, and we'll get p many. So we can get p many orthogonal eigenvectors of A. Now, so suppose they are V1A, V2A, and in this way VPA. So V corresponds V1A corresponding to lambda 1A, V2A corresponding to lambda 2A, and in this way VPA corresponding to lambda PA. And so VJA denotes the eigenvector of A corresponding to the eigenvalue of lambda J. By that I mean the corresponding to which eigenvalue it is. So suppose in our example, so A has 4 eigenvalues, 2, 3, 3, 4. So it has V1A, V2A, V3A, and V4A. So both the eigenvalues are, these two are eigenvectors. So V2 and V3 both are eigenvector corresponding to the eigenvalue 3. So we'll say that V2A is eigenvector corresponding to the eigenvalue lambda J, that is 3. Again, V3A is eigenvector corresponding to the eigenvalue 3. So in this way, so this notation is meaningful. And of course, it is to be noted that we are considering real symmetric matrix, which is a diagonalizable matrix. So therefore, or which is a semi-simple matrix. So therefore, its eigenvalues are regular, and hence an algebraic multiplicity and geometric multiplicity of their eigenvalues are same. So therefore, if so, here 3 has algebraic multiplicity 2, and hence it will have two eigenvectors, two linearly independent eigenvectors or orthogonal eigenvectors corresponding to 3, because its geometric multiplicity is also 2. Now, if we write all these eigenvectors in a matrix as a column of a matrix, then this matrix is denoted by VA. Of course, we maintain the order of the eigenvector in the sense that the first column will be corresponding to the largest eigenvalue of A, second column will be corresponding to the second largest eigenvalue of N. In this way, we'll go on. And for the jth column, the ith entry of this matrix is denoted by Vija. So again, this is a P cross P matrix. Now, if we take only the first k column of this VA matrix, then it is denoted by VAK, and we can define it for all k 1 to P, and VAK is a P cross K matrix. Determinant of A denotes, so this det A, so this denotes determinant of a square matrix A. Rank A denotes rank of a matrix A. Trace A denotes trace of a matrix, trace of a square matrix A. A inverse denotes inverse of a square matrix A if it at all exists. Now so up to this point, we'll discuss the notation about the linear algebra. Now I'm coming to the probability. So by Z, we always mean a standard normal random variable throughout this course. Capital Phi is a cumulative distribution function of the standard normal distribution. So therefore, capital Phi T is given by the probability that a standard normal variable Z is less than or equal to T. So this is the definition of capital Phi. Now tau alpha is the upper alpha point, or 100 into 1 minus alpha percentile of the standard normal distribution. So therefore, probability standard normal variable Z is less than tau alpha. That probability is 1 minus alpha, and probability accordingly probability Z is greater than tau alpha, that is equal to alpha. So therefore, so we can take equality in both the cases. That doesn't matter because standard normal distribution is a continuous distribution. So due to this property, it is called upper alpha point, and due to this property, it is 100 into 1 minus alpha percentile of standard normal distribution. So throughout this course, that we denoted by tau alpha. The next one is chi-square distribution with degrees of freedom nu. So a chi-square distribution with degrees of freedom nu is always denoted by this. So this is basically central chi-square distribution. We'll also need non-central chi-square distribution that I'm coming later. Yeah. So this is the non-central chi-square distribution. So for central chi-square distribution, we only have one parameter, that is degrees of freedom, whereas for non-central chi-square distribution, we'll have another parameter along with the degrees of freedom, and that new parameter is called non-centrality parameter. So the chi-square distribution with degrees of freedom nu and non-centrality parameter lambda is denoted by, so whatever written here, so we'll write chi-square, then degrees of freedom, then non-centrality parameter. So that needs to be in order. We cannot write the non-centrality parameter first and then the degrees of freedom. So whatever throughout this course, whenever we write the chi-square, non-central chi-square distribution, so first suffix will be corresponds to degrees of freedom and the second suffix will corresponds to non-centrality parameter square. And to ensure that it is a non-central thing, we'll write a prime as a superscript of the chi-square. So this is the notation that I will use that we'll use throughout this course. Now this notation is the upper alpha point, or 100 into 1 minus alpha percentile of chi-square distribution. So therefore probability, so if we take so it is central chi-square that is greater than the point that I'm mentioning, that one, the probability is less than, so that is equal to alpha. So that is equal to alpha. So therefore it is called the upper alpha point, and similarly probability is less than, that is equal to 1 minus alpha. So therefore it is 100 into 1 minus alpha percentile of chi-square p. Now I'm coming to the t distribution. So it is central t distribution. T with degrees of freedom nu is denoted by t nu, and similarly we'll have the non-central t distribution as well. So that is denoted by t with the suffix. First we'll write the degrees of freedom, then we write the non-centrality parameter, and we'll put a superscript prime to ensure that it is a non-central t distribution. Now this quantity is the upper alpha point, or 100 into 1 minus alpha percentile of t distribution, central t distribution with degrees of freedom nu. So therefore probability, the t distribution with degrees of freedom nu is less than tv alpha. This point will be equal to 1 minus alpha. So therefore it is 100 into 1 minus alpha percentile, and probability tv, that is greater than tv alpha, that will be equal to alpha. So therefore it is alpha, therefore it is upper alpha point of t distribution. The next is f distribution. So f distribution itself have 2 degrees of freedom. So and that degrees of freedom we need to write in order. So f nu eta is not same as f eta nu. So if we have to maintain the order of the degrees of freedom. So this is the first degrees of freedom, and this is the second degrees of freedom. And this is central F distribution. And similarly, we can have non-central F distribution. So in that case, we'll write F, then we'll write first degrees of freedom, then we'll write the second degrees of freedom, and then we'll write the non-centrality parameter with the superscript prime to ensure that it is a non-central distribution or non-central F distribution. And this quantity is again upper alpha point, or 100 into 1 minus alpha percentile of F distribution. So therefore probability, the random variable this is greater than if nu alpha, that should be equal to alpha because it is upper alpha point, and similarly probability if nu n less than if p nu alpha, that should be equal to 1 minus alpha. So in that case, we'll use this notation always. Next, suppose x is a random variable and if this f be a measurable function, so then fx is also measurable, that is fx is also a random variable, and fx with the suffix observed is the observed value of the random variable x. Consider a scalar a, so a belongs to R. So we say that a sim 0, so this sign is for sim. So a sim 0 indicates that a is close to 0. So that may be from the negative direction, that may be from the positive direction, whatever may be that, a sim 0 indicates a is close to 0. Now for any set A, this cardinality, so the mod of A denotes the cardinality of the set A, that how many entries we have in the set A. Also for two sets A and B, A cross B, this is called Cartesian product. So A Cartesian product B is given by all the ordered pair AB, where the first entry has to be from the set A and the second entry has to be from set B. So this order has to be maintained. So we cannot write a point where the first point is coming from B and the second point is coming from A. That is not allowed here. So this set allowed only the paired entries where the first entry is coming from A, the second entry is coming from B. So these are the all notation for the time being. So please be updated with this with this lecture under the heading notation. So if I include any new notation in future. So now I will discuss a few results from linear algebra and from probability, both the case, and also we'll discuss a few necessary results from the matrix derivative or something like that. So most of them you have already gone through in your previous, then last semester courses, but so this is just a recap. So first we start with basic results from linear algebra. So here with each of the result I use a number like LA1. So it will go like, so linear algebra result will go like LA1, LA2 in this way. Later we'll whenever we use these results, we call it with this name that is written first. And similarly, so this kind of name is will be also for all the result for the basic probability result uh, for matrix derivative result. So we always use some name at the beginning, and that we'll use later when we recall this result in our regression course. So let A be a n cross k matrix. The transpose of A, this is denoted by A prime. So we have already seen this notation in the section notation. So this is just a k cross n matrix, and we interchange the rows and columns of the matrix A to obtain A prime. Next is A is symmetric, is a symmetric matrix if A is same as transpose of A. And similarly, skew symmetric if A is equal to minus A transpose. But we don't need skew symmetric here. We merely need symmetric. Next result is A is idempotent matrix if and only if A square equal to A. Trace of A equals sum of all diagonal entries of A, and is denoted by trace of A. So therefore, if A is a matrix, so suppose its entries are Aij, something like that. So 1 less than equal to, so it is square matrix. Then trace of A is equal to sum of Aii, I equal to 1 to P. So sum of all the diagonal entries. Now suppose A is n cross m matrix and B is a m cross n matrix. So the product A into B and B into A both are conformable. In that case, trace of AB equal to trace of BA, and trace of a scalar A times the matrix A plus scalar B times the matrix B, that is same as the scalar A times trace of the matrix A and scalar B times trace of the matrix B. So its proof is also easy, and you have already started in linear algebra course. So basically we know that if I have to write ijth element of AB. So that will be same as A ik. So ikth element of A, then kjth element of B, then sum over k equal to, so the common index, so that is m, k equal to 1 to m. So therefore, if I write trace of AB, so that is basically sum of all the diagonal entries. So I equal to 1 to, so AB is a n cross n matrix, so I equal to 1 to n. Then ith element of AB, so that will be k equal to 1 to m aik b ki, because we need the ith element. So that basically we can write like k equal to 1 to m, then within bracket I'm writing I equal to 1 to n, then b ki, then a I k. So you can see that it is kth element of ba. So therefore it is k equal to 1 to m kth element of ba. So therefore it is trace of ab is same as trace of ba. So this is same as trace of ba. So in this way we can show this. The next one is trace of A into, so this result. So this result is very easy to show. So I'm not recalling it. If you need, you can go back to the linear algebra notes and you can see. So the next result is, so suppose A is symmetric matrix, then A is said to be positive definite if the quadratic form y prime ay is strictly greater than 0 or strictly positive for all non-zero y. So this is the definition of positive definite matrix, and A is said to be positive semi-definite if the quadratic form y prime ay is non-negative for all y not equal to 0. So if y equal to 0, then it of course 0. But so we need to mention that what happens for y not equal to 0. So for not y not equal to 0, for the positive definite matrix, we have all the quadratic forms to be non-negative, and for the positive definite matrix it has to be strictly positive. A set of vectors x1 x2 xk are called linearly independent if this equation summation I equal to 1 to k alpha xi equal to 0, this equation has only one solution, that is alpha I equal to 0 for all I equal to 1 to k. So as we know that we can frame in other way. So suppose I'm considering the matrix A whose columns are x1 x2 dot 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 xk, for example, then, and suppose I'm writing alpha equal to these coefficients, I'm taking all of them together, alpha 1 alpha 2 alpha k, I'm taking all of them together. So suppose A, so all the vectors, suppose x1, x2, xk, they are of length p. So therefore this matrix will be of order p cross k, and alpha of course is of order k cross 1. So therefore we'll have the system of linear equation A alpha equal to 0. So this 0 will be of order p. So this is a homogeneous system of linear equation, and of course it will has a solution 0, solution for alpha, but it may have more than one solution. So if it has only one solution, and that is the null vector 0, so therefore if that happens, then only the columns of A or these vectors are actually linearly independent. And rank of a matrix A equals the number of linearly independent columns or rows of a matrix A. It can be shown that the number of linearly independent columns of a matrix is same as the number of linearly independent rows of that matrix. And that common number is called rank of the matrix A and is denoted by rank of A in this way. Okay, so the next result, if A is an idempotent matrix, then rank of A equals trace of A. So that is a very important result and we'll use often in this regression course. And you can easily show it because idempotent matrix is when A square equal to A. So we have proved this in linear algebra course. So it's idempotent matrix, so therefore we have A square equal to A. And suppose rank of A equal to K. Now consider the rank factorization of A. Rank factorization of A, and suppose it is PQ. So of course, so suppose A is of order P. So of course, in that case, P will be of order P cross K because the rank is K, and Q will be of order K cross P. And as P is a full column rank, we'll have left inverse of A. Suppose it is C. And so CP is equal to identity matrix of order K. And as Q is a full row rank, so it will have a right inverse, that is suppose D. So suppose QD equal to then IK, for example. So therefore I can write, so A square is PQ. So this relation actually giving us PQ equal to PQ. Now I'm pre-multiplying with C and post-multiplying with D. So that will give us QP equal to the identity matrix of order K. Hence, trace of QP, so trace of QP is equal to trace of IK, that is equal to K. Now, what is trace of QP? So we have already seen the result that trace of AB is equal to trace of BA. So therefore, trace of QP is same as trace of PQ, which is actually trace of A. So for idempotent matrix, trace is same as the rank. And this is a very important result here. Now the next one is, suppose A be a subspace of Rk. So what is subspace? So that you can recall from the linear algebra notes. So let A be a subspace of Rk, then orthocomplement space of A is denoted by this. So this is a collection of all the vectors in Rk which are actually orthogonal to all the vectors in A. So this is the orthocomplement space. It can be shown that this is also a subspace of Rk. Now one can also show that this A, if we take sum of A and A perp, this sum is actually direct sum, and this is equal to Rk. So therefore it is called orthocomplement space of. So it's basically a complement space of Rk, and this sum is also direct. So this is called orthocomplement space of A. Now I'm taking any y belongs to Rk, then it can be uniquely, because the sum is direct, so therefore it can be uniquely expressed as y1 plus y2. So y can be uniquely decomposed as y1 plus y2, where y1 belongs to A and y2 belongs to the orthocomplement space of A. And y1 and y2 are respectively called projection of y onto A and A prime respectively. So the next one is, A is an orthogonal projector. So A is a projector if and only if A is just an idempotent matrix, but it is an orthogonal projector if and only if A is symmetric and idempotent. Now let A be a square matrix, square real matrix. Then inverse of A, that is denoted by A inverse in another matrix, another square matrix of order K, such that A inverse equal to identity matrix of order K. And if this phenomenon happens, then we say that A is invertible, but A may not be invertible always. If A is a full column rank or it is a full row rank, so if A is square, first of all, and it is a either full column rank or row rank, both are same, then A is invertible, otherwise not. Let both A and B are invertible matrices and of order P, then AB inverse equal to B inverse into A inverse. So it is very easy to see, because so if you multiply, this matrix, so AB inverse. So to satisfy this equation, what we need first, we need to write A. So A is AB here, and then you have to write what is the inverse that you are claiming. So B inverse, A inverse. So and you can see that it is the identity matrix of order P. And similarly, you can write first inverse, and then the original matrix. This is also the identity matrix of order P. So this equation is satisfied for this choice of matrix. So therefore, from that you can say that B inverse A inverse is actually AB whole inverse. And a square matrix is orthogonal if and only if A prime A equal to A prime equal to identity matrix. And in other words, we can say the inverse of that matrix is given by the transpose of the matrix. So here I have a typo, so it will be prime. So inverse of the matrix is given by inverse of the orthogonal matrix is given by the transpose of that matrix itself. The next one is, so suppose A is a K cross P matrix and P is less than K. So therefore, number of columns is less than the number of rows, and will have linearly independent columns. So therefore, it is a full column rank. So the rank of A is actually equal to P. So then the following statement holds. As you can see, so as we have discussed, rank of A equal to P, and A prime A. So A prime A will be a P cross P matrix. And so we know that rank of A prime A is same as rank of A, and its rank will be P. So therefore, A prime A will be, so rank of A prime A will be P, and it is itself a P cross P matrix. So therefore, it is a full row or column rank, and hence it is invertible. Now, column of A form a p-dimensional subspace of Rk. So each of the columns of A is basically a vector in Rk where k is greater than p. And so if we consider all the columns of A and we'll take its span, then it will form a subspace of Rk. And that subspace is basically the column space of A, and that here we denote by this notation Ca. And the corresponding orthogonal, so we know what is the column space of A. Now we'll see what is the orthogonal projector into the column space of A. And that orthogonal projector is given by this matrix. So we have already seen this in our linear algebra course when we study generalized inverse. So this is basically the orthogonal projector into the column space of A, and as you can see that this is symmetric and idempotent matrix. So why it is symmetric? So if we take prime A, a transpose of that, so as you know that AB transpose is same as B transpose A transpose, so you can write it A transpose of transpose, that is A, then A prime A inverse transpose of that, then again A transpose. Now also you know that A inverse transpose, that is same as A transpose, then inverse. So it is A, then A prime A transpose of that, then inverse, then A prime. And this A prime A transpose of A prime A is again A prime A, so therefore it is symmetric. And similarly, you can show that it is idempotent, because if you take A square, so again I have to write this to take it square. So you can see that this will cancel. So it will be A prime, A inverse, A prime. So again we'll get this matrix back. So therefore it is both symmetric and idempotent matrix. Okay. Okay. So the next one is orthogonal projector of the orthocomplement space. So we have the column space CA. Now we can have the orthocomplement space of CA. So that is CA parp. So orthogonal projector into the orthocomplement space CA parp of CA is given by I minus this matrix, whatever orthogonal projector into the column space of A, I minus that matrix. Note that again this is a symmetric and idempotent matrix. So one can show that if A is symmetric, then I minus A is also symmetric. If A is idempotent, then I minus A is also idempotent, because I minus A squared, that will give you I minus A, then again minus A, then plus A square. So A square is A, so 1A and A square will be cancelled and will remains with I minus A. So therefore, if A is idempotent, then I minus A is also idempotent. So from that property, you can say that this is also symmetric and idempotent matrix. So therefore, the orthogonal projector into the column space of A is given by this, and the orthogonal projector into the orthocomplement space of column space of A is given by this matrix. The orthogonal projector of Y belongs to Rk on Ca and Ca prime are unique, so as we have already discussed, because so if we have the orthocomplement space, then any vector in Rk can be uniquely decomposed in two parts. One is a projection from the space itself, another one is a projection from its orthocomplement space. And here the projection, these projections are given by, so y1 equal to the projection matrix into the column, into the y1 is given by the orthogonal projector into the column space of A multiplied by the vector whose projection I want to take. And similarly for the y2, that is a projection onto the C A part that is given by this. So that is the orthogonal projector. So this is the orthogonal projector onto the orthocomplement space of column space of A multiplied by the vector that we want to take, for which we want to take the projection. So here I've made a typo. So this should be actually CA part. So this is basically the projection into the column space of A and its orthocomplement space given a matrix A. Now suppose A1, A2, AP, they are columns of A. Then, so if we take the orthogonal projection of a particular column of A into the column space of A, then that will be the matrix itself, because we are taking projection into the same space. So if we take transpose of that, then we'll get here also we get transpose. This is just transpose of this thing. Now if we take projection of a column vector of A into the orthocomplement space of the column space of A, then of course we'll get 0. And this is the transpose of the third statement that we have here. So the next result is, suppose A is a P cross P symmetric matrix. So then it is diagonalizable or semi-simple. So we can, so it has spectral decomposition, and so it is also similar to a orthogonally similar to a diagonal matrix. And this orthogonal matrix is given by the orthogonal eigenvector of the matrix A, and we already denote what is VJA there. So this is the orthogonal eigenvector of A corresponding to the eigenvalues, ordered eigenvalues we have already discussed. So these eigenvectors are basically, if we take inner product with the eigenvector itself, so we'll get 1 because it is orthonormal, and also it is orthogonal. So therefore, if we take inner product between two different eigenvectors, so we'll get 0. And this matrix, of course, is orthogonal as I discussed. And this is a spectral decomposition that we have for the symmetric matrix A. And recall what is lambda A. Lambda is a diagonal matrix whose ith diagonal entries is the ith largest eigenvalue of A. So the first diagonal entry will be the largest eigenvalue of A, the second diagonal entry will be the second largest eigenvalue of A, and so on. So in this way, we define lambda A in notation section. And if we use that particular lambda A, and if we pre and multiply with the orthogonal matrix constructed by the eigenvectors of A, then we'll get A back, and that is nothing but a spectral decomposition of symmetric matrix A. And trace of A, so of course trace of A will be the sum of all eigenvalues of A, and determinant of A will be the product of all eigenvalues of A. So you can see the proof of these two statements from your notes. So basically we have to write the characteristics equation, and then equating the coefficients of lambda or coefficients of the whatever variable we have in the polynomial. So we'll get this to both this statement. The trace of A is sum of all eigenvalues, and determinant of A is a product of the eigenvalues. Next, again, A is a symmetric matrix. Then if we take the quadratic form A prime A, if we take this quadratic form, and if we take max over Rp such that A prime equal to 1, so if we consider this maximization problem, so we need for which choice of A we can actually maximize it, or the maximum attained. and this choice is given by the largest eigenvector. So this choice is given by the eigenvector corresponding to the largest eigenvalue of A. And you can see that, so if we take just max, so that will give us the largest eigenvalue. So here everywhere I have missed equal to 1. So we'll have it here. Now, okay, so before going to the part B, you may note that, so this is always the largest eigenvalue of A, but the largest eigenvalue of A can have the algebraic multiplicity or the geometric multiplicity, for example, 5. So therefore here for the argmax, so the vector which actually maximizes, or for which this maximization occurred, or this maximum value attained, so that can for that we may have the five vectors, but any one of them we can take as v1 of A. And the next one is, so suppose I'm considering all the I'm again maximizing my quadratic form, and I'm taking all the vectors for which up to the point j minus 1 will have orthogonality. Now what happens? So the next one is, so if the jth point we have the same eigenvalue like j minus 1, so suppose lambda j minus 1 is same as lambda j, then the maximum value again will be the same thing, same maximum value that we have in the previous step, and the corresponding eigenvector whatever we have assigned, that will be the maximizer. And if they are different, then whatever will be there, so maximum will not be same, and whatever eigenvector is there, that will be the maximizer. So in any way, I mean, what I wanted to say, even if we'll have multiple eigenvalues, so these statements actually make sense. And of course, the maximum value will be attained as the jth largest eigenvalue of A. That may be same as the j minus 1th largest eigenvalue of A as well, or maybe the j plus 1th largest eigenvalue of A. But anyway, these statements are always these statements are always hold true. The next result is, suppose A is a P cross P matrix and its entries are given by Aij. Then trace of A prime A, that is given by sum of Aij square. So that we have already discussed before. So I mean, the first assignment you have seen this this problem in linear algebra course. So trace of A prime A, so I have to take I equal to 1 to P, then A prime A, ith element of that. So that will be same as I equal to 1 to P, then ith element. So I'm writing Aij, then so Aij of so ijth element of A prime, so that will be basically a jith element, and then jith element again, and sum of j equal to 1 to P. So therefore it is this quantity. So basically this is sum of all sum of square of all the entries of the matrix A. So this is trace of A prime A. Now suppose A is a column vector of length P, then trace of A prime. So A prime is a P cross P matrix. So trace of A prime is same as trace of A prime A, because trace of AB is same as trace of BA. And so this is nothing but summation AI square. So here we have sum over I equal to 1 to P AI square. So this is just because A prime A is just 1 cross 1 thing. So it is just a scalar. So therefore it is given by this inner product. The next one is, following statements are equivalent for a n cross P matrix where n is greater than P. So therefore the number of rows of the matrix is greater than the number of columns, and it is a real matrix. So columns of A are linearly independent. It is the columns of A are linearly dependent. That means it is not of full column rank. So therefore rank of A has to be less than P, because the number of columns is P. And of course rank of A prime A is same as rank of A. So therefore its rank will be again less than P. And rank of so A prime A is a P cross P matrix, and it's not a full rank. So therefore its determinant will be equal to 0. That is, it will be a singular matrix. And what about the eigenvalues? So A prime is a symmetric matrix, so it will, therefore all its eigenvalues real symmetric matrix, so all its eigenvalues has to be real. and it's a semi-simple matrix as well. So we know that it has only rank many non-zero eigenvalues. And so suppose we have a 5 cross 5 matrix and rank is 2, then then the only two eigenvalues will be non-zero and the rest of the three eigenvalues will be 0. So here the rank is less than p, so we'll have some zero eigenvalues. And so p minus rank of a prime a, so whatever will be that number, only that many eigenvalues will be 0 here. That is written in the statement of E. The next result is, suppose A is an invertible square matrix of order n, and U and V are all column vector of length n. Then A U V prime, this is invertible. If and only if this is not equal to 0, and in that case A plus U V prime inverse, that is given by this thing. So this is basically Moore-Penrose inverse formula, as you know. So this can be proved basically using the partition matrix theory. So you can have A, then U, then V transpose, then 1. You can consider this kind of matrix, the partition matrix. And from the invertibility result of this matrix, you can show that if this scalar is not equal to 0, then only this matrix is invertible, and this inverse is given by this. And this is the inverse of this calculation is easy, because we will multiply this matrix by this, and again this matrix by multiplied by this A into U plus U into V, A plus U V transpose that matrix, and we will get the identity matrix back. So that part is basically very easy. So this is the Moore-Penrose inverse that also will need in the regression analysis course. So the next is basic concepts and definition from descriptive statistics that we will study. And this is a very basic, just to recap all this thing. So suppose U is a column vector of length n and V is a column vector of length n as well. Then the sample mean of U is given by U bar. So U bar is what? So U bar is summation I equal to 1 to n ui. So that is basically the 1 by n. So 1 by n I'm keeping as it is, and this sum is basically nothing but the inner product between u and the one vector of length n. And similarly, we can write the sample variance. So this is basically ui minus u bar square and sum of that and 1 by n. So that is my sample variance. So my n into sample variance I denoted by ACUU. So therefore ACUU is just I equal to 1 to n ui minus u bar square. So by notation ACUU like this, we will not have any divisor here, and the sample variance is nothing but ACUU by n. The sample covariance and the sample correlation coefficient that will define between U and V. So what is sample covariance? So sample covariance is again denoted by SUV by N, and this is given by this. So therefore SUV is just this sum, and this is given by this formula. And SUV is actually same as SVU, because a product of two real numbers that are commutative. And also the correlation coefficient, that is also RUV is same as RVU, correlation coefficient between U and V, that is given by the covariance of U and V divided by square root of variance of U and V, variance of U, and multiplied by variance of V. So this is a formula for the correlation coefficient. And the correlation coefficient is plus minus 1. It can take plus 1 or minus 1. It can be shown actually that this correlation coefficient takes value between minus 1 and plus 1 always. So both are included, minus 1 and plus 1. So when the question is when it can take the value plus 1 or minus 1. So this can happen only when U and V are linearly dependent. So therefore, one of the vector can be written as a linear combination of the other vector, or scalar multiple of other vector. If that happens, then only RUV equal to plus minus 1. So if we write U equal to some alpha times V, then only it happens. Now if the alpha is positive, then RUV is plus 1, and if alpha is negative, then this RUV will be minus 1. The next one is I'm considering 6 scalars A1, A2, A3 and B1, B2, B3 from this is scalar, so they are all real numbers. Then the following statement holds. So if we take sample mean of a1 plus a2u, that will be a1 plus a2u bar. So what will be the vector a1 plus a2u? So that will be a1 plus a2u1, then a1 plus a2u2, and in this way a1 plus a2up, sorry, un. That will be my vector. So if we take sum of all these vectors, as you can see, sum of all these vectors, so you will get n into a1 plus n into, so you will get a1 multiplied by a, because you will sum a1 n times, and for a2 you will get a2, then sum of ui. So therefore you will have, so if we take mean, so we have to divide it by n, so you will get a1 plus a2 into u prime 1 divided by n, so that is equal to u bar. So therefore mean of a1 plus a2u will be a1 plus a2u bar. That's like expectation. Similarly, the variance, this is just like the variance operator that we know in the probability class. So it is nothing but, so it has no effect in the origin change. So we'll not have a1 here. We'll only have a2, and that will be my square here. So the variance of this will be a2 square into variance of u. So variance of u is in inverse ACU that I have already written, and the scale will be come out as square. Similarly, we can see the sample covariance between A1 plus A2U plus A3B. So the sample covariance is like this. So it will not have any effect of the origin change. So only will have the scale effect of the scale. So what will be that? So we have to multiply A2 into B2, then variance of U. So you can see A2 into B2 variance of U, then A2 into B3 covariance of UV. So A2 into B3 covariance of UV, you can see, and similarly A3 into B2 covariance of VU. So that is again same as covariance of UV. So here it is, and A3 into B3 variance of VV. So here you have that. So in this way we can find out different linear combination, their covariances and variances in descriptive. So if we want to take the sample covariance, sample variance, sample correlation coefficient, so we can find out in terms of their own sample mean, sample variance in this way. The next one is matrix derivatives. So we have matrix so A, and we are multiplying it with the vector y. So we have ay. Now if we want to derivative it with respect to y, then we'll get a prime. So that is also covered in the linear algebra course. So how we can get it? So this is basically the gradient that we are calculating. So you can see that. So if you take, so suppose y is y1, y2, yn, for example. So then del y is del y1, del y2, and in this way del yn. You know that. So if we consider del yj divided by, so del yi of yj, so that will be basically indicator I equal to j. So if I equal to j, then we'll have 1, otherwise we'll have 0. So now if we consider, or if we do this, if we perform this operation here, so we'll get a prime here. So I'm not going to the details of this. You can go through the linear algebra notes here. There we have the details proof. And similarly, if we consider the quadratic form y prime ay, and if we derive take derivative with respect to y, then we'll get 2ay if a is symmetric. So there also you can see that, so you have to use that. So suppose you have yi, yj, and you are taking derivative with respect to del yk, for example, that will be equal to 2yk if I equal to j equal to k. You will get only yi if j equal to k, but I not equal to k. You will get only yj if I equal to k, but j not equal to k, and you will get 0 if I not equal to k and j not equal to k. So using this, you can split, you can write it in the several parts, and then if you derivative it, you will get this result. So I'm not going to the details of this.